is fine wherever they are, and they are following the guidelines for prevention against the spread of COVID-19. So good evening, good afternoon, good morning everyone. In this video we are going to listen to how we can derive the equation of a plane in various cases. So unlike a line, here we shall assume a plane is a surface. Any surface, it can be a chart, it can be manila, and we are going to derive its equation in a three-dimensional space. So we shall do it in various ways. First, we are going to consider a plane which has 2 points, x, y, z, that's true, and x naught, y naught, z naught, that's point P, and a vector which is normal to a plane, that's a vector n with components a, b, c. So if we assume that the portion vector of P is r naught, and that one of r of Q is r, and then we obtain a vector PQ by subtracting the components of Q from those of P, and then we say now this n is normal to the plane, so it means any vector in the plane is also normal to n. So if we dot the two vectors, the vector in the plane and the normal vector, we get 0. That's from dot product, as you can observe here. So if we dot n and p2, we get 0. So our n dot r minus r not equals to 0 is our vector equation of a plane. So let us move to the next. Here we have a scalar form of the equation of a plane. So here, if we begin from the vector form which we had, which was n with r minus r not equals to 0. You see, this one is r is a vector, a position vector of a point, r is also a position vector of a point. So like this, these are two vectors dotted together to get the vector form. So now if we substitute the components of n, which was a, b, c, and we substitute for r as x, y, z, and r not as x naught, y naught, z naught, and we dot the two vectors, we shall end up with this equation, which is a into x minus x naught plus b into y minus y naught plus c into z minus z naught equals to 0. So this is the scalar form of the equation of a plane. If we substitute negative ax naught minus by naught minus z naught with d, then we come up with a linear form of the equation of a plane as ax plus by plus cz plus d equals to 0. This is we are going to use this always as our standard form of the equation of a plane. As you can observe, the coefficients of x, y, and z are the components of the vector normal to the plane, and d can be obtained by multiplying the components of the normal vector times the components of a point which is lying in the plane. Now we are going to derive another form, this time in a parametric form. So if we consider 3 points a, b, and c, which are in the plane with components a1, a2, a3, then b with b1, b2, b3, and c with c1, c2, c3 respectively. Now in this diagram, if we take this parallelogram form to be our plane, and we assume that if a vector AC is extrapolated, we get lambda AC, and then we assume that if we multiply a vector AB with certain scalar mu, we get vector mu lambda A. This means that AP, where P is some n, is some unknown point or any point in this space, it means AP can be given as a linear combination of lambda AC and mu AB, where mu and lambda are scalars which can be determined, as we can see. So it means we can now get a vector AP as equal to mu times, that is mu AB plus lambda AC. So when you simplify this, if we substitute for the components of AP, AP is the same as OP minus A, or a position vector of P minus the position vector of A, which is P minus A. Here, AB is the position vector of B minus position vector of A, which is this, and AC is the position vector of C minus position vector of A, which is this. Then our P, if you rearrange this expression, you get P equals to A plus mu into B minus A plus lambda into C minus A. So if we substitute the components of P, which were x, y, z, because now this is in a vector form, these are vectors, so this is in vector form, this is another form of the vector form of the equation of a plane. So now if we substitute the components of P here, which was x, y, z, and we substitute the components of A, which was A1, A2, A3, and substitute the components of B, which was B1, B2, B3, and the components of C, which was C1, C2, C3, and then we get the individual values of x, y, z. We get this form, which is the form, is the parametric form of the equation of a plane. Now let us try out some example. Find the parametric equation of the plane passing through the points 1, 2, negative 3, 2, 3, 1, and 0, negative 2, 1. So we are going to assume the first one to be point A, the second one to be point B, the third one to be point C, and then we let some unknown point P, Y, Z. So if we make use of the expression, if we make use of this expression, which was the parametric form, and we where we had vector, the components of P, we substitute the x, y, z, use x, y, z. Where we had A, we use 1, 2, negative 3, and where we have B, we use 2, 3, 1, and where we have C, we use 0, negative 2, negative 1, and simplify. That's we get this, and we simplify. Now here we get the x components, which is x minus 1 is equal to mu 2 minus 1 plus lambda 0 minus 1. Then similarly for y, it is when you simplify that, get x equal to 1 plus mu minus lambda. Similarly, y minus 2 is equal to lambda into 3 minus 2 plus lambda negative 2 minus 2. So when you simplify it also, you get y is equal to 2 plus mu minus 4 lambda. Similarly here, z plus 3 equals to mu 1 plus 3 plus lambda into negative 1 plus 3. Which is this. When you simplify, you end up with this expression. So this is the parametric form of the equation of a plane. Parametric means it is in form of parameters mu and lambda, which are the scalars. So they are the so-called parameters. So if we move to the next example, we're saying find the equation of a plane through point 1, negative 1, 1, and it is normal to a vector ijk. So here we are going to assume another point x, y, z, which is also on the plane, and if we let this to be point A, and then we get AP, So it means AP will be a vector in a plane, and we shall dot it with the normal vector to get 0. That is AP dot n to get 0. But AP is the same as OP minus OA, and our OP is the vector XYZ, and OA is the vector 1, negative 1, 1. So when we substitute them in this expression and we dot with the normal vector, then we substitute, this is our OP, so our OA, and we dot with the normal vector, and we simplify, because this will be x times 1 minus 1 plus y plus 1 minus z plus 1. So when we simplify it, we end up with this expression, which is x plus y minus z plus 1 is equal to 0. That's the equation of the plane. So let's try out a third example, which is find the equation of a plane through the points 0, 1, 1, 1, 0, 1, and 1, 1, 0. So this one we shall do it using two approaches. The first alternative is to first put in the parametric form, where we shall assume a fourth point P, that is x, y, z, and then we assume that a vector AP, where A is given as 0, 1, 1, B is 1, 0, 1, and C is 1, 1, 0. I assume that a vector AP can be written in the form of a linear combination of other two vectors in the plane. It is AB, that's lambda AB plus lambda AC. So if we simplify this expression, where there is AP, we substitute there OP minus OA, and where there is AB, we put here OB minus OA, and where there is AC, we put there OC minus OA, and then we simplify. Because here now we got the components of x together, where we shall have x minus 0 equals to mu 1 minus 0 plus lambda into 1 minus 0, and simplify it, we shall get equation 1, which is x is equal to mu plus lambda. Then we similarly get the components of y and equate them. Y minus 1 is equal to mu into 0 minus lambda plus lambda into 1 minus 1. So it will also give us y is equal to 1 minus mu. Similarly, the components of z will give us z is equal to 1 minus lambda. So here we have three equations, 1, 2, and 3. So here our main aim is to get any means of eliminating the parameters mu and lambda. So there are various ways of doing that. In my case, I'm going to make here mu the subject, and I also make lambda the subject in equation 3, and the two mu I've got from equation 2 and the lambda from equation 3, I substitute them in equation 1, so that where there is mu, I substitute there mu which is equal to mu which is equal to 1 minus y, and lambda which is equal to 1 minus z, respectively. So when I substitute them there, where there is mu, I put there 1 minus y, where there is z, I put there, where there is lambda, I put there 1 minus z. So you'll get x equal to 1 minus y plus 1 minus z. When you rearrange this, you end up with x plus y plus z minus 2 equals to 0. So this is the equation, the standard form of the equation of plane. So we are going to repeat example 3 using an alternative approach. Here, in this approach, we are going to obtain, to first assume this is A, B, and C, and we obtain a vector which is normal to this plane. So by getting any two vectors in a plane, I should be able to get a vector which is normal to a plane. And once I get that vector which is normal to a plane, maybe vector n, I'll dot n times vector AP, which is equal to 0, where in AP I will have used a point x, y, z, that's for any point on the plane. So if I get a normal vector times vector AP, I should get the equation of the plane. Now, how do I get the normal vector? I will cross any two vectors which are in the plane, because if A and B are 2 points in the plane, then AB is a vector in a plane. Also, if A and C are 2 points in a plane, then AC is a vector in the plane. So if I cross these two vectors, I will get a vector which is normal to both AB and AC, and similarly equivalent, it means this vector is normal to the plane. So I will first of all determine AB, which is obtained from OB. This is OB. You can look at these components, they are similar to the coordinates we had for B, but here now this is a position vector of B minus OA. This is the position vector of point A. So 1 minus 0, 1, 0 minus this, you get this minus 1 minus 1, get 0. So this is now our AB. So similarly, you get AC, which is OC minus OA. So here you get the components, X components, subtract them, the Y components, I subtract them, and the Z components, which is 0 minus 1. I will end up with this. So now I have two vectors, AB and AC, which are vectors in a plane. If I cross them, like how I've shown in this 3 by 3 matrix, I get its determinant, where the first row is IJK, the second row is AB, the third row are the components of AC. So if we get the determinant of this matrix, we should be able to get our normal vector. So here we shall get I times the matrix of its cofactors minus J times the matrix of its cofactors plus K times the matrix of its cofactors. So when you rearrange, you shall get a normal vector as I plus J plus K. So if I dot this vector times AP, remember, which will be a form of OP minus OA. So we shall get the components of OP, which is X, Y, Z, minus the components of OA. So that we shall have some sort of X minus 0, Y minus 1, Z minus 1, which is this X minus 0, Y minus 1, Z minus 1, which are these components along the I, J, and K directions respectively. So if we dot the two vectors and simplify, we should be able to get the expression of this. You remember I dot J is 0 and I dot K is 0. So we only look at I dot I, which is 1, and so it means we shall multiply the components of I with the ones of I, the components of J with the ones of J, the components of K with the ones of K. So this is our equation of the plane as required. So we have some trial questions. You can note them down, try them please, take your time. So here the first one is P naught, which is 2, which is the first one. There's okay, there is saying find the equation of the plane passing through. So the first one we have P naught, which is 2, 4, -1, having a normal vector n, which is 2, 3. For the second one is P1, 3, 2, 2, 3, -1. So please, you can pause the video and write down these questions. There are very many. You can't read all of them one by one. However, don't forget to do the last number, number 9, after you have finished 1 up to 8. Follow this link. If you have some data, don't go there when you don't have data. Please click on this link and use this code 8140813 to play a game. It's about the equation of a plane, but it is only for those who have already registered with our Google Classroom. So in summary, we have looked at the vector form of the equation of a plane, where n is a vector which is normal to a plane, r is a position vector of any point x, y, z which is in a plane, and r naught the position vector of a known point in a plane. So we have also looked at the standard form, which is in the form of ax plus by plus cz plus d, where a, b, and c are components of a vector normal to a plane. That's the coefficient of x, y, and z are components of a vector normal to our plane. Then also d can be determined as we had shown in the steps above. Then we can also have a vector form in form of parametric form, where p is the position vector of any point in the plane, a is the position vector of a known point in a plane, and then b is also a position vector of a known point in the plane, and c is also a position vector of a known point in the plane. Then mu and lambda are scalars which can be determined. Then we also looked at, if we use now this vector form and we split the components, that's the x components, y components, and z components, we realize that we end up with a parametric form of the equation of a plane. So this is all we have seen. I say thank you for your attention, and you can access this lesson or more materials from this link, https://bit.ly/padlet. Thank you. Have a nice